well, one of the most mind-bending concepts in all of physics.
Yeah.
Quantum entanglement. We're talking about particles linked across impossible distances, seemingly communicating instantaneously. It's like the ultimate cosmic connection. And honestly, it sounds a bit like pure magic. Einstein himself famously called it spooky action at a distance.
Yeah, it's a phenomenon that truly forces us to rethink our everyday intuition about how reality actually works. It's pretty wild stuff.
Absolutely. So our mission today is to sort of untangle, yes, pun fully intended, a really fascinating question. Can the conservation of angular momentum actually offer a definitive explanation for quantum entanglement?
Right.
Can this fundamental law really explain the bizarre, spooky correlations we keep seeing?
That's the core idea our sources are digging into. What if the, perfect anti-correlations we see in entangled pairs aren't because of some mysterious instant interaction?
Yeah.
What if, instead, they're just a direct consequence of a really deeply ingrained, inviolable law? The conservation of total angular momentum. Think of it like this. Instead of trying to figure out how particles are secretly sending signals, that'd be a bottom-up approach, looking for a mechanism.
Right, like a hidden message.
Exactly. This is more of a top-down explanation.
Yeah.
It focuses on the universe's sort of ironclad overarching rules, like a cosmic budget, you could say.
A cosmic budget. I like that.
Yeah, the particles must obey these rules, and their correlations are simply a consequence of these fundamental constraints, not some, secret messaging system.
Okay, that top-down idea is pretty intriguing. So to really get it, we need to start with something that might sound a little abstract, but it's actually foundational. Symmetry. In physics, symmetries aren't just about things looking pretty or balanced, are they? They're like fundamental constraints on how the universe's laws work.
Precisely.
When we talk about symmetry, we mean transformations that don't actually change the laws of physics themselves. It's almost like the universe has certain settings that are always the same no matter what you do.
Yeah, exactly. These principles of invariance, they're really cornerstones of theoretical physics, and the precise mathematical link between these symmetries and conservation laws, well, that was unveiled back in 1918 by the brilliant mathematician Emmy Noether.
Ah, Noether's theorem.
Her theorem, Noether's first theorem, it's honestly one of the most significant results in all of theoretical physics. It's huge.
So it's not just an observed pattern like noticing that energy happens to be conserved. It's deeper. It's an unavoidable consequence, like the universe just has to conserve it.
That's basically it. Noether showed something quite breathtaking. If you have a system and its fundamental description, think the Lagrangian kinetic minus potential energy, doesn't change when you do something continuous to it, like rotate it or shift it in time, then there must be a quantity associated with that system that stays conserved. It's this deep mathematical connection between what stays the same, the symmetry, and what must be conserved, the conservation law. Think of it as the universe's internal bookkeeping ensuring balance.
This idea of symmetry, maybe it sounds a bit abstract, but it's where our deep dive into entanglement really starts to get fascinating, right?
Definitely.
One of the most fundamental symmetries is rotational invariance, or the isotropy of space. This just means the laws of physics are the same, no matter how you orient your experiment in space. Turn it sideways, upside down, the laws don't change.
Right. And the amazing thing is, this principle holds true even if the object itself isn't symmetric at all.
How so?
Well, think about a jagged, completely asymmetrical asteroid tumbling through space.
Okay.
It still conserves its angular momentum perfectly. Not because the asteroid itself is symmetric, it clearly isn't, but because the laws governing its motion are completely indifferent to its orientation. They just don't care which way it's facing.
I see. The laws are symmetric even if the object isn't.
Exactly. The underlying structure of space dictates the conservation.
So, if these fundamental symmetries are the universe's unshakable rules, and Noether's theorem translates them into conservation laws, what's the big consequence when we apply it to something as universal as rotational symmetry?
Yeah.
The idea that space looks the same whichever way you turn.
You directly get the conservation of the total angular momentum of any isolated system.
There it is. Angular momentum.
Yeah. And in quantum mechanics, this isn't just some casual observation. It's like written into the very DNA of how quantum systems behave. The total angular momentum operator commutes with the Hamiltonian, which is the quantum way of saying it's a constant of motion.
Meaning it absolutely does not change.
For any isolated quantum system, yes. This gives the conservation of angular momentum its inviolable status. It's not just an observed regularity. It's a necessary consequence of the universe's rotational symmetry. It's a fundamental constraint that any viable physical theory has to respect.
Okay, so we've established this incredibly powerful, unbreakable law rooted in something as basic as symmetry. Now, let's bring back the main event, the cosmic magic trick itself, quantum entanglement. What exactly is it in a way that helps us bridge this gap?
Right. Quantum entanglement is, well, it's a defining feature of quantum mechanics and a really profound departure from classical physics. It describes two or more particles linked in such a way that their collective quantum state, you just can't describe it independently for each particle, even when they're separated by huge distances.
Okay.
The key here is that even if you have maximal knowledge of the whole system, you still don't necessarily know everything about its individual parts. Not until you actually look, until you measure.
So it's not like that classic analogy, I think it was John Bell who used it,
Right.
about Bertelsmann's socks, where someone always wears mismatched socks, and you see one is pink, you instantly know the other isn't pink.
Small chuckle. Yeah, Bertelsmann socks.
That's just pre-existing information, right? You knew he always wore mismatched ones.
Exactly. Bertelsmann socks are a good starting point, but they're almost, well, boringly classical compared to entanglement. Those socks had their definite colors before anyone looked.
Right, one was pink, one was, say, green from the start.
With entanglement, it's more like neither sock has a definite color until you look at one, and then instantly the other one somehow snaps into its complementary state no matter how far away it is. That's the really mind-bending difference.
Okay, that's weird.
Yeah. Classical correlations, like the socks, rely on information that was determined beforehand, local information. Entanglement, however, describes correlations that are much stronger, quantitatively stronger than anything you can explain with such pre-existing locally held information, what physicists call local hidden variables.
And the classic example here, the one that really ties into angular momentum, is the decay of a spin-zero particle, like a neutral pion decaying into an electron and a positron.
Yes, that's the quintessential example. The law of conservation of angular momentum dictates that if the total spin of the parent particle is zero before it decays, the total spin of the daughter particles must remain zero after the decay.
Makes sense. 0 equals 0.
Right. Now, for two spin-12 particles, like an electron and a positron, there's a unique quantum state that sums to zero total spin. It's called the spin singlet
A
state.
singlet state.
And this state is a quantum superposition. It means basically particle 1 is spin up and particle 2 is spin down, or our particle 1 is spin down and particle 2 is spin up, both at the same time. Neither particle actually has a definite spin direction until you perform a measurement. They are literally undefined in that property.
So what's the immediate consequence when we actually do measure these particles? Let's say we measure the spin of the electron along the vertical axis.
If you measure that electron spin along the vertical axis and find it up, then the positron, no matter where it is guaranteed to be found down if you measure it along that same vertical axis.
Guaranteed. Instantly.
Instantly, as far as we can tell. The moment you measure one, the shared quantum state collapses, or seems to, and the other state is instantly determined relative to the first. Perfect anti-correlation.
And does this only work for vertical? What if we measure horizontally?
That's what's truly crucial here. The spin singlet state itself is rotationally invariant. It looks the same mathematically no matter how you rotate your perspective.
Ah, like the laws of physics earlier.
Exactly. So this perfect anti-correlation holds for any measurement axis you choose, vertical, horizontal, diagonal, anything provided. And this is key, provided you measure both particles along the same axis.
Okay, same axis, perfect anti-correlation. But you mentioned earlier the correlations are stronger than classical. Where does that come in?
That comes in when you measure along different axes. That's the real quantum punch, the part that truly defies classical intuition.
So Alice measures vertically, Bob measures horizontally. Something like that.
Precisely. When you measure along different axes, the correlations don't just disappear. They follow a very specific quantum mechanical pattern. It depends on the angle between the two measurement axes. There's a trigonometric relationship, like The probability of both being up might be related to the sine squared of half the angle.
Okay, getting technical, but the point is it's a specific pattern.
It's a specific non-classical pattern, and it's these correlations, when measured along different axes, that cannot be reproduced by any classical model based on pre-existing properties and local influences. That's what eventually led John Bell to his famous inequality.
Bell's theorem.
And the experimental violation of Bell's inequality demonstrates conclusively that no classical local realist explanation, like Bertelmann's socks with hidden instructions, can account for quantum correlations. That's where the truly non-classical nature, the real spookiness, is revealed.
Okay, so this brings us smack back to our core question. Can the conservation of angular momentum be a definitive explanation for all this weirdness, especially the perfect anti-correlation part?
Let's revisit the core argument from our sources. The idea is that those perfect anti-correlations, when measured along the same axis, aren't some mysterious superluminal influence. They are a direct, necessary, and almost mundane consequence of the inviolable law of conservation of angular momentum.
How so?
Well, if a spin-0 particle decays into two spin-12 particles, the total spin must remain 0. So if you measure one daughter particle and find it has a spin of, say, plus h2 along some axis,
The other has to be Metagen 2.
it must manifest a spin of micro 2 along that same axis. There's no other option if the total is to remain 0. It's like a cosmic ledger. The numbers always have to balance instantly.
This is where that top-down explanation really comes into its own, isn't it? It sidesteps the need for a mechanism.
Exactly. It's not trying to describe a specific physical influence traveling between them, which is what always leads to that spooky action feeling.
Right, the how.
A bottom-up or causal mechanical explanation would try to find that physical chain of events, that signal. But the conservation-based argument operates at a completely different level. It doesn't need to posit a mechanism.
It just says the rules demand it.
Pretty much. It explains the phenomenon by subsuming it under a more fundamental principle. It's a global constraint inherent in the structure of the system and the laws governing it, not a local cause propagating from one particle to the other. The correlation must exist because the structural constraints of the universe demand it.
It's like saying the total money in your bank account has to stay the same. You don't need to know the exact path every single penny took to know the sum is conserved.
That's a great analogy. The conservation law dictates the overall balance, regardless of the specific transactions.
So how does this reframe the famous EPR paradox? Einstein, Podolsky, and Rosen wrestle with this idea of separated particles influencing each other.
Well, from this perspective, it's not really about Alice's measurement causing Bob's particle miles away to suddenly flip its state. Instead, the perspective is that the two particles were never truly independent entities to begin with. They are components of a single unified quantum system described by the singlet state.
Components of one thing.
And that system state, the whole state, is globally constrained by a shared conserved property. The total angular momentum must be 0. So when Alice measures her particle, she's simply revealing information about the state of the entire system.
Not changing Bob's particle directly.
Her result instantly implies the state of the other component, Bob's particle, not because of some superluminal signal flying between them, but because their fates were linked, mathematically constrained, from the very moment of their creation by this unbreakable conservation law. They were always destined to show opposite results if measured the same way.
Okay, that's a very compelling, almost elegant way to look at the perfect anti-correlation part.
Yeah.
But it feels like we need to push it harder. The biggest challenge, the biggest gauntlet for any explanation of entanglement is Bell's theorem.
Absolutely. You can't talk seriously about entanglement explanations without confronting Bell.
Our everyday intuition about the world, it relies on two core assumptions, right? Locality and realism. Can you break those down quickly?
Sure. Locality basically means no influence travels faster than light. An object is only directly affected by its immediate surroundings. What happens over there can't instantly affect things over here. Standard cause and effect.
Makes sense. And realism.
Realism is the idea that physical systems possess definite properties before and independent of whether we measure them. Like the moon is still there even when nobody's looking. Or Bertelmann's other sock had a definite color already. This often implies the existence of hidden variables that determine these properties.
Okay, so local realism is basically common sense.
Yeah.
Things have definite properties, and nothing travels faster than light.
Pretty much our classical worldview. Now, John Stuart Bell, back in 1964, did something incredible. He proved mathematically that any theory based on these two assumptions, local realism, would be limited in the strength of correlations it could predict for entangled particles.
These are the Bell inequalities, like a speed limit for classical correlations.
Exactly, a mathematical boundary. But here's the kicker. Quantum mechanics itself predicts violations of these Bell inequalities. It predicts correlations that are stronger than any local realist theory could possibly allow.
And the experiments.
That's the crucial part. Starting seriously in the 1970s with Aspect and others, and culminating in truly sophisticated, loophole-free experiments in the 2010s, the results are in. Rigorous tests have consistently confirmed the predictions of quantum mechanics. They do violate Bell's inequalities.
Meaning our universe.
Our universe does not adhere to local realism. At least one of those intuitive assumptions, locality or realism, or maybe both in the way we understand them, has to be wrong.
Wow, that's a huge implication for our conservation law explanation, isn't it? If local realism is dead, what does that mean for conservation of angular momentum explaining entanglement?
It means the conservation of angular momentum in entangled systems cannot be understood as a law that is satisfied simply by local pre-existing properties, like the colors of Bertelsmann's socks being set at the factory.
So the law still holds, but not in the simple, local way we might have first thought.
Correct. Bell's theorem doesn't refute the conservation law itself that's incredibly well established. Instead, it reveals its true, radical nature in the quantum realm. It forces us to conclude that the conservation of angular momentum, when applied to entangled systems, must be understood as an inherently non-local phenomenon.
Non-local?
Yeah.
So somehow connecting distant particles without a classical signal.
Yes. It's not just a passive bookkeeping rule summing up pre-existing local values. It has to be seen as an active, non-local constraint that somehow governs the outcomes of measurements as they happen, ensuring the total conserved quantity is maintained across space-time in a way that defies any classical local causal explanation. The law isn't just describing what happens, it seems to be actively enforcing it non-locally.
Okay, so the conservation law acts non-locally, but what does that actually mean? Does it depend on how you interpret quantum mechanics itself? This feels like we're hitting the interpretation problem.
You're absolutely right. While the conservation law provides a powerful constraint, what it constrains and how that constraint operates depends heavily on your chosen interpretation of quantum mechanics. The explanation isn't interpretation neutral. It frames the problem, but the picture you paint depends on your philosophical stance on quantum reality.
Can you give some examples, like how does Copenhagen see it?
Sure. In the standard, or maybe traditional, Copenhagen interpretation, properties like spin direction literally don't exist until measured. They're brought into being by the act of observation.
So there's no pre-existing value to conserve locally.
Exactly. In this view, the conservation law acts as a constraint on the possible outcomes of measurements. It's more of an epistemological rule, a rule about what we can know or observe. If you measure one particle up, the rule says the other must yield down if measured the same way. It avoids explicit non-locality by denying that the particle had a definite state before measurement. Reality is created by observation, constrained by conservation.
Okay, what about something like many worlds, MWI?
Many worlds takes a completely different approach. It claims the universal wave function is objectively real, and all possible outcomes of a quantum measurement actually happen, each in a separate branching universe or world.
So when Alice measures...
As the universe splits, in one branch, Alice measures up, and, constrained by conservation, Bob measures down. In another parallel branch, Alice measures down, and Bob measures up. The conservation law holds perfectly true within every single branch.
Ah, so it structures the branching process.
Precisely. It ensures conservation is maintained in each emergent world. There's no spooky action within a world because all outcomes consistent with conservation simply occur, just in different realities. It's like a perfectly choreographed quantum play happening simultaneously on infinite stages.
Okay, that's one way to preserve the law. What about something like Bohmian mechanics, pilot wave theory? That one sounds deterministic.
Bohmian mechanics is fascinating because it is deterministic, and it does assume particles have definite properties, positions specifically, at all times. But to achieve this and match quantum predictions, it has to be explicitly non-local right from the start.
So it embraces non-locality.
Fully. It posits a pilot wave or quantum potential that guides the particles. This pilot wave is influenced by the positions of all particles in the system, no matter how far apart. In this view, conservation of angular momentum is dynamically enforced by these non-local equations of motion. The correlation isn't mysterious or probabilistic, it's the result of this precisely choreographed non-local dance where the particles' trajectories are instantly interconnected to rigidly uphold the conservation principle across the whole system.
So the takeaway seems to be, the conservation law is fundamental, it always holds, it dictates the perfect anti-correlation. What it means for reality, whether it's a rule about knowledge, a constraint on branching universes, or enforced by a non-local wave, depends entirely on the interpretation you pick.
That's exactly right. The conservation law tells you what must happen, but its ontological status, what it's actually a law about in the real world, differs radically, depending on your framework for reality.
Which brings the deeper philosophical point, doesn't it? What is the status of these physical laws anyway? Are they just descriptions of patterns, or are they something stronger?
Yeah, that's a great question. The philosopher Mark Lange made a really interesting distinction, he asked. Is a law just a description of a regularity, maybe even a cosmic coincidence that just happens to hold true everywhere we look? Or is it a genuine constraint on possibility, something that holds with a stronger kind of necessity, dictating why things must be this way, like a metal law governing other laws or events?
And the law of conservation of angular momentum,
Yeah.
given its origin in Noether's theorem and symmetry, feels much more like a constraint, doesn't it?
I think that's the argument, yes. Because it's a direct mathematical consequence of a fundamental symmetry of space-time itself. The isotropy of space, it's not just an accidental pattern. It functions as a powerful constraint and reveals why the world must exhibit this particular conservation irrespective of the messy details of specific interactions.
It has real explanatory power.
Exactly. It tells us something necessary about the structure of reality. The correlation isn't just a fact about how particles happen to behave. It's a necessary feature of any universe whose physical laws don't care about direction. This gives the conservation-based explanation its profound force.
Okay, this all sounds incredibly solid, almost definitive for explaining that perfect anti-correlation. But you mentioned there's a potential wrinkle, a recent challenge. Something about conservation laws maybe only holding statistically.
Ah, yes. This is a more subtle point that's come up in discussions about quantum measurement. Some interpretations or ways of looking at measurement might suggest that in an individual quantum measurement event, a conserved quantity like angular momentum might appear to momentarily jump or not be strictly conserved for the particle itself.
That sounds like it would completely undermine using it as a definitive explanation if it's not conserved in each event.
Right. If that were the full story, it would be a major problem. But the resolution, according to deeper analysis, is that this apparent non-conservation in individual measurements is actually a kind of optical illusion.
An illusion? How?
It arises because you're treating the measured system, the entangled particles, as truly isolated during the measurement process. But, of course, a measurement is an interaction.
It involves a measuring device, at the very least. The observer, the apparatus.
Exactly. You can't realistically isolate the particles from the thing that's measuring them. And here's the remarkable part. When you consider the full entangled system, which includes not just the original particles, but also the measuring apparatus they interact with, the conservation law, is found to hold exactly and rigorously in every single individual instance.
So the jump in the particle's angular momentum is compensated somewhere else.
Perfectly compensated by a corresponding change in the angular momentum of the measurement device itself or the broader environment. The total angular momentum of the particle plus apparatus system remains constant throughout the interaction.
Wow. So to explain the entanglement using conservation, you actually need to invoke more entanglement between the system and the measuring device.
It's this fascinating recursion. Yes, for the conservation of angular momentum to definitively explain the entanglement between the particles, you ultimately have to account for the unavoidable, deeper entanglement of that particle system with its measurement context. The explanation requires acknowledging that the measurement itself extends the entanglement. It's like peeling an onion, only to find more onion underneath. The conservation law holds, but its application becomes more complex and encompassing.
Okay, so let's try to wrap this up, recapping the strengths. The conservation of total angular momentum is incredibly compelling as an explanation for the perfect anti-correlations in entanglement. Why? Because it's fundamentally grounded in the universe's symmetries via Noether's theorem.
Right, it's not ad hoc.
It has immense explanatory power as a top-down constraint, telling us what must happen. And it describes a physical necessity for those observed correlations rooted in the isotropy of space.
It correctly identifies what must happen if you measure along the same axis. It provides the mathematical structure for that perfect anti-correlation.
But we have to acknowledge the weaknesses, or maybe the incompleteness, right? It's not quite a definitive physical explanation in the sense of a complete blow-by-blow causal story, especially when you get to measurements on different axes and the Bell violations.
Exactly. It's ontologically incomplete. It doesn't by itself tell us how nature enforces this constraint, especially in a non-local way that violates Bell's inequalities. That how still depends heavily on interpretation. And as we just saw, the deeper complexity involving the entanglement with the measurement device hides beneath the elegant simplicity of the initial idea applied just to the particles.
So maybe the best way to put it is that the conservation of total angular momentum is the indispensable structural boundary condition for any valid explanation of entanglement.
I think that's a very good way to phrase it. It's the precise mathematical articulation of what is being non-locally enforced in the quantum world, at least for same-axis measurements. It perfectly frames the mystery of entanglement, even if it doesn't fully resolve the how of non-locality.
Which leaves us with a final thought, maybe a provocative one for you, the listener.
What's truly fascinating here is that while this fundamental conservation law tells us precisely what must happen in certain situations, the mechanism, the how nature pulls this off non-locally, remains the central, unresolved puzzle of quantum foundations.
Yeah, the answer you find most satisfying seems to depend entirely on the kind of reality you're willing to embrace. Is it a world of inherently probabilistic collapses?
Or constantly branching parallel universes where all possibilities happen?
Or maybe a deterministic but profoundly non-local choreography guided by hidden waves?
This deep dive into just one scientific concept, conservation of angular momentum, leads us straight into the deepest, most challenging, and honestly most fascinating open questions in all of science.
Yeah.
What is the fundamental nature of reality, and how on earth does it actually work?